Look at a modern smartphone in isolation. It is a sealed glass rectangle, but activate it and it instantly connects to an invisible grid of global infrastructure, pulling down data from servers thousands of miles away in milliseconds. That connection is built on a strict engineering compromise. To achieve true portability, designers sacrifice physical space, thermal cooling capacity, and battery size. Everything inside the chassis is a concession to footprint. CompTIA A+ objectives 1.2 and 1.3 test your ability to manage those compromises. You need to know how to connect these physically constrained devices to external networks and provide comprehensive application support. We are going to build this ecosystem from the inside out. We will start with the internal hardware footprint, move outward to local and global wireless connections, and finish with the software protocols used to secure the device at an enterprise level. Your objective as a technician is specific. You must take a highly restricted, vulnerable consumer device and configure it to act as a secure, desktop equivalent workstation. Effective support involves verifying every layer of the architectural stack, from internal physical components to the software governing external network access. Crack open a modern laptop or tablet, and you will see that physical space is the ultimate limiting factor. The internal real estate is packed to the millimeter. This density introduces high fragility. Trapped heat degrades performance. Electrostatic discharge can easily arc between tightly packed components, and the fragile ribbon cables routing data require specialized spudgers to disconnect safely. Standard desktop components simply do not fit. System memory must be packaged into small outline dual inline memory modules, or SODIMMs, which lay flat against the motherboard to shave off vertical height. Power delivery faces the same physical limits. With no room for a bulky internal power supply, mobile devices rely entirely on specialized battery chemistry to operate away from an outlet. Standard lithium-ion batteries provide reliable power without the memory effect of older cells. But for ultra-thin laptops and modern tablets, manufacturers use lithium polymer. LiPo batteries can be manufactured in flexible, flattened shapes to fill whatever void is left inside the chassis. Thinness also eliminates room for input and output ports. To connect multiple monitors, external keyboards, or hardwired networks, you must bridge the device through an external port replicator or a dedicated docking station. Every component selection is a calculated trade-off. You are trading raw processing power and physical connectivity for a lighter, smaller footprint. Once the internal hardware is established, the device needs a way to communicate outward. Its longest range connection is to the global cellular network. This graphic breaks down the authentication process. To access the cellular network, the hardware requires a subscriber identity module, or SIM card. This chip identifies the specific device to the carrier and proves it is authorized to consume bandwidth. The chip stores the phone number, subscriber data, and the unique encrypted credentials required to establish a secure link with the tower. Over time, the physical footprint of the SIM has shrunk to match tighter device tolerances. As shown here, they progressed from the standard size down to micro, and finally the nano SIM used in most modern phones. We are now seeing the transition to the eSIM, which eliminates the physical card entirely by embedding the authentication module directly onto the motherboard. Once authenticated, the connection speed depends on the carrier technology. Legacy 3G networks topped out around 7.2 megabits per second. 4G LTE pushed that to 300 megabits, while modern 5G architecture allows for download speeds up to 10 gigabits per second. Without valid subscriber credentials, the physical hardware cannot interact with the global telecommunications infrastructure. Consider a common field scenario. You have a laptop that requires internet access to reach corporate servers, but you are in a remote location with no local Wi-Fi available. You can bridge the laptop to the internet using a mobile device's established cellular connection. This process is called tethering. For the most stable connection, use a physical USB cable. You can also initiate a Bluetooth connection for a steady, lower-power data link. The third method, a Wi-Fi hotspot, allows multiple separate clients to connect simultaneously. Activating a hotspot reconfigures the device to operate as a miniature wireless router for local clients. Tethering acts as a critical bridge. It leverages existing cellular infrastructure to bypass the local hardware limitations of laptops or tablets that lack their own built-in cellular modems. The connectivity radius scales down even further into extreme close-range device-to-device communication. Near-field communication, or NFC, relies on very short-range radio waves. By design, the transmitting and receiving chips must be within a few centimeters of each other to complete a circuit. This proximity requirement makes NFC highly useful for secure data transfers, like executing contactless point-of-sale transactions or instantly exchanging the encrypted pairing data required to establish a Bluetooth connection. With overlapping cellular, Wi-Fi, Bluetooth, and NFC signals broadcasting constantly, there are times when you need to immediately sever all external connections. Airplane mode serves as a master hardware switch. Toggling it instructs the operating system to power down the cellular, Wi-Fi, Bluetooth, GPS, and NFC radios simultaneously. From a troubleshooting perspective, you can override this state. Individual radios, like Wi-Fi, can be selectively re-enabled manually, while the master airplane mode keeps the cellular modem disabled. Technicians must be as proficient in isolating these network layers as they are in establishing them. Managing physical radios is only half the equation. In a corporate environment, IT departments must govern how software interacts with those hardware connections. Mobile operating systems utilize a sandbox architecture. Applications run in strictly isolated environments. They cannot pull GPS coordinates or activate the camera unless the user explicitly grants those privileges. To control those permissions at an enterprise scale, organizations deploy Enterprise Mobility Management, or EMM software. EMM encompasses several distinct protocols. Mobile Device Management, or MDM, focuses strictly on the hardware layer. IT uses MDM to enforce strong lock screen passwords, mandate device encryption, or issue a remote wipe if the physical unit is lost. Mobile Application Management, or AMM, targets the software layer. It allows administrators to update, configure, or restrict specific corporate applications without interfering with the user's personal apps installed on the same phone. Finally, Mobile Content Management secures the actual data, applying strict encryption and sharing policies to proprietary corporate files. EMM bridges the gap between consumer design and corporate requirements. It takes highly portable, inherently vulnerable hardware and layers on the strict policies required to process sensitive data. We have mapped out the modern mobile architecture, from the internal motherboard to the external management server. You know that strict physical limitations dictate the use of flat SO-DIMM memory, specialized thin chemistry batteries, and external port replicators for desktop expansion. You know that a SIM card authenticates the hardware to global cellular networks, and that tethering can bridge that connection locally via USB, Bluetooth, or Wi-Fi hotspots. And you know that protecting the data traversing those networks relies on operating system sandboxes and centralized EMM profiles. When troubleshooting mobile issues for the A+ exam, you must systematically isolate each of these layers. You are verifying everything from the physical seating of the SIM tray up through the enforced software policies. Supporting these systems requires understanding how these layers intersect. Professional mobile support is the practice of maintaining the secure link between constrained hardware and the global network.